All right. So we have talked about hydrocarbons. We've watched a video on the different, not necessarily fractions, but the different types of alkanes, right? And I don't know if you recall, but the small alkanes like methane and ethane are found as natural gas. Propane is also a gas. But when we get to butane, and I need a new lighter because my other one was not working, butane is a liquid when compressed a little bit. But then we get to pentane, and it's a liquid, and hexane again is a liquid, and then we get up to gasoline and all those things and all those fractions that we saw. So it turns out that hydrocarbons can be gases and liquids and solids, but their melting points are quite low. All right. So for physical properties of hydrocarbons, they have no dipoles and are non-polar. Now, those are two terms that we used back when we were talking about molecules. We looked at the electronegativities. We looked at these numbers that described how they shared their electrons. And the carbons and hydrogens share quite equally. So they don't have a little charge on them. It means they don't have any dipoles. They're non-polar. That means they don't stick together very well. And if they don't stick together very well, they have low melting points and boiling points. Another property, they evaporate very quickly. Acetone is a hydrocarbon. It's used in nail polish remover. It's kind of like gasoline. If you get acetone on your hand or gasoline on your hand, it feels cold. Have you ever noticed that before? If you ever get nail polish remover or something on your hand, it feels cold for a very brief moment in time, and then it's all gone. And that's because it evaporates very quickly. So hydrocarbons tend to have very low melting points. All right? Now, we can have really heavy hydrocarbons like asphalt, or what do they call it, bitumen in the video. And they're solids, and they have a higher melting point, but not nearly as high as things like metal, right? Tungsten's melting point is like 3,500 degrees Celsius. You know, hydrocarbons would have been long burnt and destroyed by that temperature, okay? Sodium chloride or ionic compounds, also very high melting points, into the thousands of degrees. You do. You want it to vaporize so it can burn. We'll talk about that in a moment. So, low melting points and boiling points. Let's get into the reactions of hydrocarbons. We're going to learn about three main reaction types today. The first reaction type is combustion, which means they like to burn. So, combustion reactions. We talked about this at the very beginning of the course when we were looking at the Bunsen burner. Complete combustion, where there is an adequate supply of oxygen and the only products are carbon dioxide and water. The color of the flame is blue. Incomplete combustion, when the oxygen supply is limited and there are other products like carbon or soot and carbon monoxide produced. Soot, not super dangerous. You don't want to inhale a lot of it. That wouldn't be a good thing to do, to have that particulate solid black stuff in your lungs. Carbon monoxide, very dangerous. The reason carbon monoxide is very dangerous is because it's chemically similar to oxygen molecules. And when you inhale carbon monoxide, it enters your bloodstream and takes the place of where an oxygen molecule should go. So as you keep breathing it, you're not getting oxygen to your cells, and your cells suffocate. And, you know, if you were to inhale a lot of carbon monoxide over a large period of time, you would die. You would suffocate. So incomplete combustion is dangerous. So here's an example. Let me get the gas on here. And like I said, oops, not that one, that one. And like I said, we've seen the Bunsen burner, and this is just a big burner. It's got many little tops on it, so there's lots of tips of inner blue cones, so I can heat something really hot. And it's big, it's cool. So this is burning with lots of oxygen. The air openings are open. It's blue. It's producing carbon dioxide and water. Those little yellow flecks, that's actually iron from the barrel. So if I give the barrel a shake, it releases some iron from the barrel itself, and then that glows at whatever its flame color is. But if I were to choke off the oxygen like this, oh, there we go. So if I prevent the oxygen from coming in, you can see there we've got a yellow flame. It looks pretty, but it's incomplete combustion. That would have some soot with it. Remember when we put the test tube in it, it made the test tube black? So there's the soot. And it would also be producing a little bit of carbon monoxide. In terms of our demonstration here that I did for you already once, and because it's fun to just blow something up, we'll do it again. We're going to do this reaction tomorrow. We're going to take some of this calcium carbide tomorrow, and we're going to produce some of this gas to test. The gas that's produced is ethine, all right? And ethine is also known as acetylene, and we're going to study the acetylene tomorrow. We're going to study the way it combusts, kind of what I did here, except a little more controlled. And we're also going to study some other reactions that it can undergo, and we'll talk about those later on. But like I did last time, if I take just a little bit of the calcium carbide, and remember, I don't know if you recall, I don't want too much. I want the right amount, and that's what makes this a tricky demonstration. It's fun. I put the top on, and I make sure I have a good spot so I don't, you know, put it right through the light. And if we have enough oxygen, hopefully we get lots of complete combustion. That's fun. So there we had. Is it in there? What's the? There it is. So that was complete combustion. We had a good amount of oxygen with the fuel. And now if I take lots, and this is what I did last time to try to get you guys all excited, what if we did it with all kinds of stuff? And you guys thought I was going to blow the whole place to pieces, but you already know what this is like. This is going to just produce a nice little flame, poof. And that's incomplete combustion. How do you know that this is incomplete combustion? Yellow flame, yellow flame. It's also producing some soot. We can't see it, but there's black that is rising to the ceiling because it is incomplete combustion. There's not enough oxygen. That's fun. Leave that right there. Okay. So let's do some combustion reactions. So let's say I give you a question like this on a test, and I ask you to do a balanced chemical reaction for the complete combustion of, and you're wondering, how do I balance that up? How do I do that? Well, the easiest way to deal with this is to take the structural formula and turn it into a chemical formula, putting all the C's and H's together. So what would this be? C2H6 plus O2. Now, if it's complete combustion, what are the products? CO2 and H2O. CO2, oh, I should have left some room to balance, and H2O. All right? So when I'm asking you to do a combustion reaction of a chemical, draw it out, turn it into a formula, and then just balance like we've balanced, before. Start with the C's. I'm going to pick on Bethany because I haven't done it for a while. How many C's have I got here? So how many carbon dioxides do I need? Well, how many C's are in the carbon dioxide? There's only one. So how many of these do I need? I need two. I need two because there's two of those. And because it's just fun to pick on her, there's a 6 right there. So there's 2 H's in each of these. So how many of these do I need? 3. Someone's helping you out there. Say thank you. Yeah, that's good. So now how many O's do I need? Now you might need a decimal, and it's okay if you need a 0.5. Have you figured it out, Conrad? What do I need? Well, look at how many O's have I got here? 2 times 2 is 4. And how many are in here? 3 times 1 is 3. So I need 7 O's, but I've only got O2's. So how many O's do I need if I could have a fraction? 7 divided by 2. 3.5. 3.5. And don't worry about the 0.5. Leave it. If you're balancing combustion for me on this test, leave it. Even if you're balancing combustion on the exam for that, you can leave the 0.5. Normally we would double everything, but that's okay. Tells us I need 3.5 O2s. So for this one, C2H2, again, O2. It's complete combustion, CO2 and H2O. And we balance again. How many C's? The number of C's is going to be the same as the number of CO2s that you need. The number of H's, right? You're going to need half the number of waters. So how many C's? 2. How many waters? 1. So that's 2 times 2, that's 4, that's 1. So I need 5, that's 2.5. Okay? 2.5. So that's how we write a combustion reaction for our organic compounds. If it is incomplete combustion, I would have to tell you a little more information, and I'll explain why. Are you good to go? Okay. Oh, let's not do that one. Let's go ahead and do incomplete. No, because there's other types of reactions to do. I've still got to do a reaction called substitution and then addition reactions. So in this case, I've said that there's some CO and some C and then some water. And the amount of C and CO depends on how much oxygen there is. If there's a little more oxygen, then a little more CO would be made. If there's a little less oxygen, then a little more C would be made. So you need to be told a number in order to balance this. Or I need to take away one of these things. So let's assume then, for no particular reason, that 2 COs were formed. And now we can balance the rest. So I need to tell you a little information in order to do that. Because if then I've got 2, how many C's am I going to need to balance out my 6? Right, so I've got 2 C's there. There's 6 C's there. How many carbons am I going to need to balance out the carbons? I'm going to need 4. And now I can balance my hydrogens. How many waters will I get? 7. And now I can balance my oxygens. I have 2 oxygens in the carbon monoxide, Gee, I hope you're doing a lot of math back there, Felicia. Excellent, good. You're calculating O's, were you? There's a lot of keystrokes for adding some O's. 7 from here. Total of 9 O's. So what do I need there? Yep. 4.5. 4.5. 4.5 times 2 is 9. Yep.
So only this type of like thing you can decimal?
Yeah, that would be nice. Only this one. You know what? If you were to leave a decimal in a hurry and you didn't double something up, I'd give you full marks. It's not proper balanced chemical equations, but when it comes to like doing stoichiometry, a 0.5 works just fine. It's still, and the argument when we teach you in grade 9 and 10, well, you can't have half of an O2. That's what we would say in grade 9 and 10. But you know what? Mathematically, in reality, I can have half of an O2. That's an oxygen atom. There's nothing wrong with that. So, yeah, if you had a 0.5 in there, it would not hurt things. Yeah.
And it does work out.
Sure it does. In stoichiometry, if you double everything, you then have a ratio of, say, 2 to 4 versus 1 to 2, and a 2 to 4 ratio is the same as a 1 to 2 ratio. So, yeah, it doesn't make any difference. Doesn't matter. Okay. So, combustion. We okay with the fact that we can burn these things? Excellent. Now let's move on to, wait a minute. Oh, yeah. Let's move on to some reactions that are specific to alkanes and specific to alkenes. Because I don't know if you noticed in the combustion ones, I had an alkane, I had an alkene. This stuff that I burned here was ethine. It doesn't matter whether it's an alkane, alkene, or an alkyne. They all burn. Now I want to talk about a reaction that's specific to alkanes, and then a reaction that's specific to alkenes and alkynes. So, the first reaction is called a substitution reaction. And you just have to write it all down. It's just information about a substitution reaction. So this says H atom. I don't know if it's, would you say an H atom? Is that the way I should do that? Maybe put an N there if you like. But I'm talking about a hydrogen, all right? That doesn't say atom. Right, see what I'm trying to say there? Is replaced by another atom or groups of atoms. Substitution reactions are slow and require a great deal of energy to break the bond between carbon and hydrogen. The single bond between carbon and hydrogen is quite strong. It can be overcome by heat. That's what happens when we combust it. We're blowing the molecule to pieces. But in a reaction like this, we're not blowing the molecule to pieces. We're trying to be careful and trade out an atom. Now you might ask, why would we want to trade out a single atom in a chemical like that? Well, all of the organic chemicals that we've kind of talked about in our list of different types, medicines and plastics and all that stuff, have slight variations in the atoms that are connected to them. So if we can pick off a hydrogen and maybe put on a chlorine or a bromine, we can change the properties of the chemicals. We can change it from being a useless, hunk of stuff to being a useful piece of plastic that has all these special properties. a classic example. I might have the timing wrong. I want to say the Second World War, might even be in the time between the First and Second World War. I think it's during the Second World War. All of the rubber that they had for things like tires was made from natural rubber trees. So a tree that produced this sap that was very sticky and rubbery. And so it was natural rubber. But as the war went on, they needed so much rubber, they were running out of rubber for tires. So chemists were beginning to try to make synthetic rubber. One of the first types of synthetic rubber they made really didn't have any structure to it. It was goopy, it stretched, it didn't have any form to it. A chemist actually took that formulation and sold it as silly putty. Have you ever seen silly putty? It can bounce. If you pull it too hard, it breaks. But if you pull it slowly, it stretches. It has all kinds of interesting properties. Not good for tires on airplanes and Jeeps because it would not hold its form, but as a toy, an awesome thing. By changing some of the atoms in the plastic, switching a few things out, the rubber's properties changed, and we now have synthetic rubber, which we all use on our tires, et cetera, et cetera. So that's why we want to be able to slowly swap out certain atoms in a reaction like this. Alkanes are relatively unreactive, but will react slowly with halogens in the presence of ultraviolet light to produce alkyl halides. So UV is the same stuff that burns your skin, right? Ultraviolet light. Yep. Is ultraviolet light really warm? No, but it would warm your skin if you absorbed that light, but it doesn't necessarily have temperature itself. Sorry? They use it to cure a plastic, but that's not necessarily, it's not because of its temperature. It's because of its chemical properties. Okay, so let's draw a reaction for a substitution reaction with bromine. In order to do this, we want to draw out our chemicals. CH plus, and then the bromine I'm going to just write as Br2. All right? Now, the two reactions that we're going to use can be easily explained by an analogy, a simple story. And I'm going to use hockey because, well, who's the greatest sport on earth? That's just the way that goes. So in hockey, if you're playing 5 guys, you got your goalie, full strength, you can't just add someone onto the ice because then you'll have 6 and you will get a penalty. And as a coach who has run the door for many years, I've taken many penalties as people tried to get on the ice and we haven't taken anyone out. So if you want to swap out a player, you first have to remove one so that you can put one on. What do you call it in sports? Call it a change, but there's actually a technical term for it. What do you call it in basketball if you want to trade somebody out? A substitution, right? It's the same in hockey. You're doing a substitution. This is a substitution reaction. So what's going to happen is, when you're done the substitution reaction, one of the H's will now be a bromine because you've plucked off an H and the bromine has gone in its place. And you can think of the other Br as maybe being the bench because now the H goes with the Br onto the bench and we have a successful substitution reaction. And this takes place when we have UV light shining on it. Okay? Oh, he's taking it too far. Don't go too far. Now, if the UV light keeps shining, this reaction will keep on going. All right? If there's enough Br around, a second substitution will take place. Okay? Now we've substituted 2 because now another substitution went on there. And in the end, I'm just going to put here, etc. It would end up like this. All right? all of the BRs swapped out for the H's. It would have taken 4 BR2s, and it would have produced 4 HBRs in the end. Okay? So a substitution reaction will keep going until everyone is swapped out, but the key for this is that this is slow. This is a slow reaction. It takes a long time for that substitution to take place. Yep? I tend to just have you add 1, right? Or perhaps I give you this as the reactant and you add 1. You see what I mean? I wouldn't make you write it all out. Because you could imagine if I gave you something like this, there would be 2, 4, 6, 8, 10 steps to that. And I'm not going to make you do that. I just want you to know what a substitution is. Okay? This can be with chlorine instead, and you'd have a Cl on it. In tomorrow's lab, we're going to do it with iodine and see if we can get it to add on. But the key is, it's a slow reaction. It does not happen very quickly. Okay? All right. So that's a substitution reaction. I'm going to do one more here. And I'm only going to do the first substitution. And this time I'm going to write it as a condensed structural formula because writing it all out can be a pain. And there is no way to know which H gets swapped out. There's no way to tell which one gets first. One molecule, it could be an end one. The other molecule, it could be one in the middle. So it doesn't really matter where you put it. I'll just put it on an end one because there's actually twice the chance of having it go on an end one because there's 2 ends and there's only 1 middle, right? So CH, now I'm going to turn that into a 2. Now you could put an I right beside it if you'd like, but just to show that we've stuck an I on it, I'm going to put it down. That's not any special thing. You could put it up. You could put the I in behind the H. That would be acceptable. But I'm just putting it down just to say that we've stuck it down there on the bottom. I'm not done. There's still one more product. What's the other product? Where did the H go that left? With the other I that didn't get stuck on it, because only one I gets on it. So that's then HI. And again, UV light is needed for that to take place. That is a substitution reaction. When you have an alkane, which is all single bonds, that's what it can do.
Okay, I was thinking that actually was the whole time, but I don't get it how there's 3.
Oh, that's a screw up. That's me. That's me. That's me. CH2, CH3. That's just me. That's me. Yep. No, that's good. That's good. That's me. You gotta catch that. It's not you. That was me. I was busy worried about talking about where to put the I, that it doesn't matter. I forgot to write the third C. No, it didn't magically turn into an S. No, we didn't lose that there. That's correct. Good job. All right? Okay with that? So alkanes undergo substitution reactions. Click. So now let's talk about what if they have double and triple bonds. And again, our sports analogy will serve us well for this. And it actually doesn't work for like basketball and volleyball. The nice thing about basketball and volleyball, the term is actually substitution, okay? But you know what? In hockey, you are actually doing a substitution as well because you have to remove one before you can put one out. Now, with alkenes and alkynes, remember, they're not saturated. They're unsaturated. So it's as if they've got some H's missing. And in my sports analogy, that kind of works because in hockey, if you get a penalty, you actually remove a player from the playing surface. Basketball, it doesn't work that way. You get fouls. There's no fouls in volleyball. So hockey is actually really the analogy that we need. So when you have a penalty, you've got one of your things missing. When you've got an alkene and an alkyne, you have H's missing. It means there's room to add on. Now in hockey, you've got to wait for the penalty to be over so that you can add your player back. Then there's where the analogy ends. But that's what we can do with alkenes and alkynes. We can add things to them because they have double and triple bonds. They have room for more things to go on. So we're going to be doing addition reactions. Now, it turns out that the double bond and triple bond of an alkene and an alkyne are quite weak. They're like add-on bonds on top of a single bond. If you were to take the 4U, you would learn in great detail how that works. The first bond of a double bond is just like a single bond. It's the same thing. It's the second bond that is added on top of it that is actually weaker. And when you put a third bond on it, it's just as weak as the second bond. So they're easy to break. The second bond of a double bond and the third bond, second and third, of a triple bond are weak and easy to break. And therefore, alkenes and alkynes exhibit greater chemical reactivity, and their reactions tend to be fast. They're faster than alkanes because of that weak double bond and weak double and triple bond.
Temperature probe?
They went. Pete has them.
He has some
He's building.
stuff.
Yeah, he's building houses. Yeah. Do I have thermometers? Yep. Just one?
Who was asking a question
About UV light? No, we needed. It was part of the lesson. We need UV light in order to do a substitution reaction. Oh yeah, yep.
Right.
Okay. How are we doing? Yeah, you can. Yeah. We're not going to name those, but you can have more than one double bond in a chain. You can have a double bond and a triple bond in a chain, and their names can be done. We did that in the 4U, but we're not going to name them here. You're ahead of the game? You're done? Nice. Okay, so let's do some addition reactions. Oh, I should have left some space. That's okay. Just write the first one. Just write the first one.
Like the number one having to be that important, right?
In that we can add this, or this. Yeah, it is. Yep. So I wanted some more space because I wanted to use one of these pictures to show you what's happening in this reaction. I may clear the screen and then rewrite it. You might want to write twice. So here we've got an alkene. This is ethene, and it's got a double bond. Now, I tried to mention as you were writing there, you need to think of a double bond as being made up of a single bond, like the first thing that connected the C's, and then the double bond was like added on second. That's not really the way it works. But the second bond of a double bond, that second bond, is the weak one. And so what happens is the bromine can come and react with it, and the bromine would sit maybe like this, all right? So here we've got the Br and the Br. And what happens is the bond opens up and makes new connections with the Br, okay? So we get a connection in there and a connection in there. So in the end, I'd have a bond like this and a bond like this. And that double bond is now broken. So it's C, single bond C. We've got H2 and H2, but now we have a Br there and a Br there. All right? The reason I kind of drew it like that is because I want you to imagine the Br2, which is connected together, comes up to that double bond, hits it, and single bonds are connected to them. You know what, to be honest, you don't even need to write that if that makes sense to you. You could just write that equation right there and you'd have it correct. I don't need to see what I drew here on a test or a quiz or on an assignment. I'm just trying to get you to visualize in your mind that if there's a double bond, this Br2 will stick right on top of that double bond, and they'll attach to those C's, and the double bond will open and break and connect to the B's. Okay? All right? We okay with that? Now, the confusing thing about this is, notice our reactants were the same as in a substitution. But the difference is I have a double bond. So if I have a double bond, it's not a substitution. We add both Brs on, and there's no other product. In a substitution, it's an alkane, all single bonds. Only one Br sticks, and the H goes with the Br for the other product. Do you see the difference kind of between those two? So as soon as you see a double or triple bond, you're adding, you're not substituting. Okay. Now, in this case, there are two bonds to be broken. I like to think of them as being the top bond and the bottom bond, and that's actually closer to reality than you think. The middle bond you can think of as the single bond. It's holding on really tight. And so notice now we're going to have two H2s. One's going to attach there. The other's going to attach there. And I'm going to end up with a CH and a C, and now with an H down there and an H down there and an H up there and an H up there. And then still here I have, oh, sorry, there, I got scribble, scribble, scribble. I thought maybe I was at the end, but that has an extra carbon on it, right? And then CH3. Okay? I didn't see that carbon there either when I was busy writing. So we've added them onto the bonds. Think of it like breaking the top bond and the bottom bond. Now notice when I add H's, they're not like bromine or chlorine. So you actually could write this then as CH3, CH2, and CH3, right? Because we can put the H's all together. And what is this called with all single bonds and 3 carbons? What's it called? What's this going to be called down here? Sorry? Propane. Propane. What was this stuff called to begin with? Propyne, because it had the triple bond in it, right? So we turned our propyne into propane by adding H's to it. Okay? And I've got a couple more examples because we can add a couple more different things. How are we doing? What's that? Yeah, it's that. It's the what am I thinking of? It's the calcium carbide that's still reacting in there a little bit. Okay. So like I said, 2 more examples. So here I've got some 2-butene. And as soon as you see the double bond, you're thinking addition. We're going to add to that. Yep. Do those need to be balanced? Yeah, they do, but they tend to balance themselves out. You'll notice in the previous one, I added 2 H's. Did you see on your, I'm not going to go to the previous slide. And that's because I needed to add an H2 on one bond and an H2 on the second bond. So when you're adding to an alkene, you only need one of them. When you're adding to an alkyne, you'll need 2 of them because they're going to add 2. That's how it balances.
What would you call that little thing that you add? Like what's that?
There's really no name for it. There's really no name for it. What's that? That's me thinking. That's my brain. There's really no official name for it. The first example were the 2s, right? The Br2, the Cl2, the I2, the H2. This is now 2 different atoms, but we still can add them straight on. That's what we're trying to get across to you. That I can simply take it and add it. All right? So in this case, CH3. Now, what do you want to put on this one? And you know what? It doesn't really matter which way you do it. It gives you the same molecule. So if we do it this way, and the H ends up on this one, what am I writing here? CH2, because there's an H there, right? CH2. And what am I writing on this one? What's stuck to it? A C. A Cl. You can put it down if you want, or you could put it in line as in CHCl. But I'll put it down just so we can see where it came from. CHCl. Because Cl is different than an H, eh? So I want to keep it kind of separate. And then our CH3. And I apologize to video watchers that squished weight off to the side, but I ran out of room. Yep. You mean put the H down here so that you can visualize the addition? That would be awesome. No, I'm not concerned. It doesn't have to be all a condensed structural formula. You can demonstrate to me what's adding there. That's great. That would be maybe even better. It doesn't matter to me. Okay? So there we're adding a hydrogen and a halogen. There's actually a name for this. It's called hydrohalogenation, which the 4 U's have to memorize and all that other good stuff. I don't need you to name that. I do have one more. And I know it's been a little bit of a long lesson, but we're getting there. The last one is adding water. You can actually add water to these. This has its own name as well. And it's actually, and you guys don't need to know the names other than addition. That's all I expect you to know. But this one is quite a logical name. When you need water and you take in water, what are you doing? Hold off there, veteran. What do you call it when you, oh, I need water, and then you drink water in? What are you doing to yourself? You're hydrating yourself. This is a hydration reaction because we're hydrating the molecule. We're adding water to the molecule. We can actually make this reaction go in reverse. I'm not going to teach you that reaction. That's for the 4 U's. But if you make the reaction go in reverse and you take water away, what do you think that reaction is called when you don't have enough water? Dehydration. That's a dehydration reaction. Yep.
So like when it's the 1, 2, and 3, like adding H2O.
Yep.
For the last one, is HCl and HBr the only 2 options? Or is it anything like that?
It could be HI, but I probably wouldn't give you that. No, it could be any of those halogens.
Like any, okay.
Yep. Yep. Okay. And you know what? We have to treat it like HOH, and this is really like the last one. The hydrogen is going to go to one, and the OH is going to go on the other. All right. So I don't know if I want to draw it out. Maybe I can. So HOH, and this is going to form a bond over here, and this is going to form a bond onto the O. Again, you don't have to draw that out. So you get an H on one and an OH on the other. So CH3, CH2, and I'm going to put the H down so that you can see it. And then CH2, and then an OH on that. So we've now got an OH hanging on that branch. Thank you. And then a CH3, CH3. So we have an OH on it, all right? No, because the double bond has broke, right? Because we're doing an addition reaction. The H goes on the one and the OH on the other. This family of chemicals right here is called an alcohol. So when you have an OH on a carbon, it's what we call an alcohol, and the alcohol that's in beverage alcohol is related to those as well. We'll talk about more functional groups on Monday after our lab. Okay, so those are addition reactions, and that's what happens when we have double and triple bonds. I'm not going to talk about the test for saturation right now because I've gone plenty long enough. We're going to do a lab tomorrow where we talk about a test for saturation, and we'll write this down tomorrow. We'll talk about it tomorrow. So worksheet is again online, and as you know, there's the worksheet, and then there's the second half of the assignment, and it's like the worksheet. It's based on today's lesson, and as Mark would, you'll go straight to the assignment because I'm not marking the worksheet. Okay, Felicia would do it too. Okay, you all would do it. Anyway, just letting you know, you now can do the assignment, and I'm marking that one. Yep. Yes, you can. Yeah, let me just get this thing stopped recording here, and then we got it.
So like this.